Okay, let's moving on to the next topic. All right, gentlemen, got a question for you real quick. I want you to look at yourself in the mirror. Look at yourself into the mirror. Okay, and ask yourself from the scale of 0 to 10, how hot you are. How hot do you think you are? Let's do that. 10, I mean you are Chris Hemsworth. 0, you are Jabba the Hutt from Star Wars. Yes. So if you ask me, I know I'm 11. And okay, what I want to say is, human like us, we put scale on everything. Right, on everything. Come on, in school, we talk about how hot you are from scale of 0 to 10. Have you ever had like a girl talk, guys talk? Oh, come on, we all have that, right? In school, girls walk by, we were like, hey, dude, look at that girl. She's hot. Your friend will be like, how hot she is? 11, 12. Yeah, we put scale on everything. So that's a hotness. We put scale on weight, right? We get on scale. The what else? So balance in the laboratory. Okay. We put scale on a temperature. We have degrees Celsius, Fahrenheit, Kelvin. Okay. So basically, we put scale on everything, even acidity. All right. And the reason for that, for chemists, chemists deal with a lot of solutions. Some are more acidic than the others. Being able to measure the acidity of the solution provides some benefit. I'll give you some example. Okay, so to measure the pH of water in the river, it tells you the environment surround that water. Is that clean? Is that habitable? All right. The pH of your blood or your urine tell you the health-related issue that could happen in your body. What else? Food and drink, yes. All right. Tell you if it's safe to drink, is it drinkable or eatable. All right. Detergent, alcohol wipe this day. All right. So be able to measure the pH of this solution or this product tells you its usefulness. And lastly, we got medicine. So the pH of the medicine kind of tell you the effectiveness and safety of each medicine. All right. Back in the old time, so Dr. Sorensen, he's a Danish chemist. He's famous for the introduction of the concept of pH as a new way to measure acidity in the old time. Okay, let's be familiar with the pH scale real quick. So it starts from 0 to 14, but it doesn't mean it stops at 14. It can go above that or can go below 0. Right? Some solutions have negative pH, even more acidic than 0. All right, and let's see. So if I want to take this example of solution we're going to talk about now. How do we put this liquid or solution into the pH scale? Well, think about it. pH tells you acidity, how acidic or basic, depends on how you look at it, same thing, of each solution is, correct? Well, what makes solution acidic? What makes compound acidic? What compound makes this solution acidic? Well, there's only one compound we talk about, proton or hydronium ion, right? The concentration of proton or hydronium ion. All right, if you know the concentration of hydronium ion or proton in each solution, you can calculate pH. Does it make sense? Okay. Now, the reason we have the pH is if you look at the concentration of proton right here, of course, mentioned earlier that concentration of proton tell you how acidic each solution is, right? But the concentration is a little bit long and it's not convenient to look at it, right? We try to make it a small, simple number. Okay, we try to make all this concentration of proton, make it like a simple number. So Dr. Sorensen came up with the new way to express the acidity of the solution by call it pH, right, or pH scale. And he defined that pH is negative log of concentration of the acid, proton or hydronium ion. For example, the pH of water, which is neutral, right? If you guys know it's 7. pH of water is 7. So take negative log of the whole term right here. Don't forget the parentheses in your calculator, all right? So you're going to get 7. That's it. Alright, this is what I want you to do. So pause the video. It should take you like maybe 30 seconds. I want you to calculate pH of all this guy right here. All the three solutions right here. We have ammonia, wine, and milk. Now let's do it right here. Alright, once you've done that, let's check with me, okay? So the pH of water is 7, so I'm going to put water in onto the pH scale, so in 7 right there. Now, the pH of ammonia solution, this is a basic solution, right? So negative log of 4 times 10 to negative 12, you should get 11.4, so about this one is basic, all right? Now, we're going to go to wine down here, so wine. So negative log of 3.2 times 10 to negative 4 molar is 3.5. So wine is actually a little acidic. And last one, milk. So the concentration of proton is right here. Negative log of it, 6.5, close to water, almost neutral. That's it. That's how we learn about pH scale. All right. Let's see if you get this concept test. Which solution would have a lower pH? They have the same concentration. If you take a look, right, 1 molar, 1 molar. You can do the equilibrium like in chapter 15. Calculate the concentration of proton in equilibrium, and then you can calculate pH from there. But hey, we don't have to do that. Just compare. Same concentration, but they dissociate differently. Hypochlorous acid dissociate much more than that's about 1,000 times than hypoiodous does, right? So if you do Ka, you can see obviously 10 to the negative 8, 10 to the negative 11. So which means that hypochlorous acid is a stronger acid. With the same concentration, the stronger acid dissociate more, produce more concentration of proton. The pH of this solution is going to be lower. Okay? Alright, that's the pH. Alright, we're going to use this in the practice in the next video. Alright?